source of knowledge and inspiration all through my career up till now. I am to mathematics here in Brazil. When I finished my studies I was finishing my studies in an engineering school in France, and I had many projects for myself. Of course, not mathematics was not among these projects. And then Le Drapier said, would you like to go to Rio? Yeah, of course. He said, but you will have to do mathematics. I said, yeah, so of course, why not? And I came here, and Jacob kind of forced me to have a career in math. And the books by De Mello also were part of this, so I hold them responsible, the three, for what happened to me. But I don't hate them for this. So Jacob was telling me immediately that he was from Lebanon, as I was. And I say, okay, great, now. Proud of Jacob as Southern Hemisphere. And I wish Brazilian mathematics continue thriving and to have future, as well as I wish mathematics in what we still call the south part of this world to thrive and progress as much as possible. And I hope that this ICM, that was a kind of coronation of all these efforts to push forward the mathematics in the southern hemisphere, will have a great impact in this direction. So thank you, Jose, thank you, Jacob, thank you, the organizers, for this occasion. It's an emotional occasion, and I'm deeply touched to be here talking in this kind of occasion. So, as you know, Wellington had a deep passion for one-dimensional quasi-periodic dynamics. So I decided to give a talk on one-dimensional quasi-periodic dynamics, although much simpler than the occupation. And for many people who were at ICM Congress and already heard a lot of talks, take it as a recreational talk where things will be rather sit back, relax, and enjoy. So, I'm talking about random walks. It's a joint work with Dima Golgopiak and Masha Capriti. Maria Capriti. So, are the people in front hearing me too loud, or the people behind not hearing me at all? I continue like this? Yes. Okay. So, what's a random walk on Z? A random walk on Z is diffusion process, discrete, by which the point moves either to the right or to the left, and we are here concerned with a nearest neighborhood transition. The simple random walk is given by a pair P, Q, such that P plus Q is equal to 1. P is the probability to go to the right, Q is the probability to go to the left. You all know that such walks have an asymptotic limit law. It's called the central limit theorem, by which the walker at time n, if we call Zn the position at time n, if he starts at 0, then Zn divided by sigma square root of n converges to the normal law. Okay? Now we can sophisticate the example a little bit by letting the probabilities Pi and Qi depend on the set I where the walker stands. And this becomes a random walk in a random medium if these Pi and Qi are picked randomly. distribution. When this distribution of Pi is Qi is compactly supported in the interval 0, 1, we call the walk random walk in random environment elliptic. So Pi random in epsilon 1 minus x. The behavior of such a walk is important as a mathematical object, but also for physics, statistical physics. You have it portrays the diffusion of a particle submitted to random force in a one-dimensional environment. There is also an equivalent formulation in quantum mechanics for a particle under random potential. Now, studies about this walk were very active since the 70s. Solomon first showed that if log Pi minus log Qi, so this is random, huh? And IID, I'm supposing them IID now, okay? Yes? So if this is 0, this is an if and only if the walk is recurrent. Of course, the medium being ergodic, you have the law of large numbers. And people were wondering what can be said further. And then Sinai came, great dynamicist, and surprised people by showing a very strong phenomenon. It's now called Sinai subdiffusion or slow diffusion. He showed that this would converge to some law. Yes? So it's very peculiar. You added randomness, and what you get is a new normalization, which is much smaller. Diffusion is much smaller to some law. This law, so Sinai found this in 82, and this law was later discovered explicitly, independently by Golozov and Keston. Okay, what next, right? What next? For mathematicians, they always like to do more theorems. So the community started thinking about the higher dimensional problem. And it turns out that the higher dimensional problem is extremely hard. It's extremely hard. So high dimension is you have a Walker in Z2, and transition probabilities up, right, down, left are themselves IIDs, and you want to know what happens. Do you have slow diffusion, or do you regain the normal central limit theorem kind of square root n? The idea is that in dimension 1, what gets you to the slow diffusion is barrier potential, where you get some resistance to walk. But in higher dimension, you will have a resistance when you try to walk in some given affine direction. But people believe that you will always, the walker will always find a way to find a breach in these barriers and will diffuse much faster. But nothing is known. What Sinai again did, he said, okay, I'm going to study now another model where we put some less randomness on the Pi Qi. So the new model is we take Pi and Qi quasi-periodic, and this will be my subject. So you can take Pi as equal to some function P of theta plus I alpha. And here theta is in the torus and alpha is irrational. results become like with probability such and such on theta for Lebesgue measure, the Walker at time n will be there or here. Okay? And what did Sinai do? He showed that if alpha you follow me, huh? I'm now talking about Zn. It's the position of the Walker when theta is fixed. So, for example, you want to understand what happens Zn in some interval. Yes? You want to know what happens. And Sinai, he showed that if alpha is Josephine, then CLP goes. So again, what does it mean? It means that Zn minus NV divided by square root n some sigma converges to the normal distribution. So the idea here will be that V will be V equal to 0 if and only if the integral of log V minus log Q d theta is equal to 0. So Sinai is saying that if alpha is Josephine, the walk is the usual simple random walk. 1/2, 1/2, or 1/4, 3/4. It depends on this integral. Now, you may wonder what happens for UV Walker. You may also wonder, which is also a very yet more interesting problem, what happens if we have a quasi-periodic walk on Z2? So quasi-periodic walk on Z2 will be just here you have theta plus I alpha plus J beta. Okay? It will be the probability Pij. And then you have Pij, Qij, Sij, Tij, and their sum must be 1. Right? But this is the problem. And notice here that the dimension is not on the torus. This is not very important. I could replace here in these theorems T by Td. Here it's the dimension on the action. It's Z2 action on the circle that you will consider if you want to go to higher dimension ZD action. And it is much more complicated. It's something like when you compare studying the Schrödinger operator in one dimension or in higher dimension. I mean, it's a completely different world. And the tools that work, all the dynamical system tools that work for studying the Schrödinger operator in one dimensional, in 1D, fail in higher dimension. Okay, so this is an interesting problem. It has to be studied. For example, try to think that when alpha and beta have full measure, the walk will behave like a simple random walk in Z2. This is not known. Many questions can be asked, but what we did is deal with the remaining case, which is the 1D case, and alpha is UV. So so I remind you that alpha is Josephine, alpha is UV if for any n that exists P and Q, such that alpha minus P and Q is less than 1 over n.
No, 1 over Q to the n, right?
Yes. I added another parameter. Okay, thank you. Of course, UV numbers have zero measure, so you may say, why, what for are you studying them? But they also are residual first category set, so they deserve some attention, our attention. And what we must say, here I must add that, so this is called P in C infinity symmetric. Okay? I call C infinity symmetric when this integral is 0. Asymmetric is when the integral is not 0. So, when P, there is another theorem I wanted to mention before I say what we want to do, by Dolgopiat and Golchi. It says that if P is in C infinity asymmetric, then there exists always a quench central limit theorem. So if for any x there exists Bn of x, some drift, such that Zn minus Bn of x divided by some sigma square root n converges to the normal distribution, and this is so x here is fixed, okay? So it's Px for the probability Px, okay? This means that the asymmetric walk, whether alpha is for any alpha irrational, the asymmetric walk always has a quench limit CLT. The Diophantine walk, these quench limits, they all hold for the same Bn, which is n times V. Okay. Now what happens for UV alpha? So, symmetric or asymmetric has geometry, say symmetric. Let's start with symmetric. Erratic What do we mean by erratic statistical behavior? We mean, first of all, that the variance, okay, will oscillate wildly. Variance oscillates
approximation to the variance.
What?
The variance is not the approximation of the variance.
What do you mean by?
I mean, the variance is takes account of everything, so it's not something dynamic.
Variance like V theta n. So you take the theta of Zn. Okay, you fix theta, you look at Zn, it's a random walk, you take its variance. This, as a function of n, oscillates. Sometimes it will be like Sinai subdiffusive walk, logarithmically bounded, and the walk is logarithmically confined, localized, and sometimes it will be like the CLT of order n. And sometimes, we didn't prove it yet, but we believe it's correct, sometimes it will also get close to n squared, which is the maximum it can be. For a nearest neighborhood walker, it cannot be more than. And then the drift also oscillates between, so drift can be minus n, plus n, 0, etc. as a function of n. And this for a walk, you fix alpha uv, and then for a generic walk p, for a generic medium p, given by the function p, here you put some topology on the smooth functions, and you get first category set for which all this is true, that the walker will contain in his, say, DNA for various types of time, various periods, very different behavior. By the way, suppose alpha is uv, but for very long scales of time, and the renormalization of alpha, you see bounded coefficients successively, consecutively. Then alpha will behave almost like a Diophantine number during some time. And therefore, Sinai's law, Sinai's observation on Diophantine alpha will apply. And the walker will be for long moments behaving like a simple random walk with the usual CLT, the square root n CLT. But then later he will become confined in a logarithmic scale because he will meet potential barriers in trying to walk on the right or the left. I will explain all this. 3, and this is the most striking thing, is that no quench or annealed limit distribution. So this is very different from the asymmetric case, because in the asymmetric case there is always a quenched limit. What I'm saying here is that no matter how you choose your drift, no matter how you choose the renormalization here, you will never get a limit in distribution. Why? Because you will have moments where you are localized, other moments where you are behaving as a CLT. Now when you are localized, like log n localized, doesn't mean you don't have a limit law that is normal. It may be that dividing by some power of log n, you get a limit law that is normal. But what we show is that when you try to divide, when you try to normalize, you get Dirac masses. At other moments, you get normal law. And that means there is not a single limit law that holds, okay, for every n. So let me just be a little bit more specific. And the fourth thing I wanted to add is that for generic P in C infinity asymmetric, you have to accept that this exists, but what you know is that no annealed limit holds. The annealed limit is when, so this is Px for distribution when x is fixed. The annealed is when you put distribution here, you accept randomness in x. So it's a limit when x is random and the walker is random. So here you must put Lebesgue, okay? Okay, how much time do I still have? I don't know. 10? Ah, okay. Okay. Anyway, you stop me when you want. No, okay. Now, no? I want to give the flavor of the point. So the theorem is that for any UV, for d delta dense symmetric, I will not talk about the asymmetric case anymore. That's what I did. There exists tk, sk, rk, going to infinity. These are sequences of time. And for tk localization, so for tk, we will have that ztk IL for almost every x. For almost every x. So the tk, sk, rk depend on x. For almost every x, the probability in x that ztk be bigger than log tk squared is less, say, than 1 over 1 over log tk, or 1 over the square root of tk. It doesn't matter. So this is just saying that with very high probability, at time tk, the Walker is in a small interval. Small, I mean, logarithmic. 2, we have one-sided drift. So here, at time sk, the Walker will start imitating a random walk with drift. This is surprising because the Walker is symmetric, right? So he will do like this. There will be mu k that is of order, say, almost sk to the power 1 minus any epsilon, such that ztk minus mu k divided by square root tk, some sigma sk. Okay?
ZSK or ZTK?
ZSK, of course. Thanks. This is like normal distribution. What about the third type behavior? Is the one that will imply absence of any limit, completely erratic, is the two-sided drift. So at time rk, well, there will exist bk in, say, bk of order t of order rk to the power 1/4, such that z rk minus bk is less than epsilon bk, I think. Much less than rp. Okay. So, what I'm saying is this. The Walker starts at 0. There exists bk here and minus bk here. And with probability 1/2, the Walker will be here in a tiny interval of logarithmic scale, actually. No, in a tiny interval, this interval is much smaller than bk. Or here, in an interval that is much smaller than bk. So, the spread is like 2bk. So if you want any limit law, you need to divide by something like bk at least, right? If you want some limit law, you need to divide by bk. But if you divide by bk, the support on the right is much smaller than bk. So you get a Dirac mass. And you get another Dirac mass here. And that's why, if the Walker on some time scales will behave like a simple random walk, and if a limit law exists, it should have been the normal law, but on other time scales, the limit law must be derived. So there is no possible limit law. And this argument works for annealed as well as for point. Okay. Now, how all these things are proved, and why is it simpler in dimension 1 than dimension 2? Because in dimension 1, you have something like a tool. It's a magic martingale. Well, first of all, let me talk about invariant distribution. So we say the walk has an invariant distribution if there exists a row in, say, row from T to R, a density function that is invariant. This would be P of theta minus alpha rho theta minus alpha plus Q of theta plus alpha rho theta plus alpha equals rho theta. Right? Because you have the density at theta. Invariance means this density is equal to whatever can come from the right or the left. And this is what is coming from the right. This is what is coming from the left. Now, Sinai proved that if alpha is Diophantine, D has a smooth solution. And if the walk is asymmetric, also D has a solution. But we are talking about P. Okay. Why? Actually, you make a change of variable, you put Q of theta, rho theta equal G of theta, and you see that if it's okay, and now this has a solution, requires that the integral here of the logarithm must be 0. But it's not enough, and what helps is that when alpha is Diophantine, you overcome the small divisors, yeah? The small divisors coming from resonant multiples of alpha will not hurt you if this right-hand side is smooth. But when alpha is UV, it is not the case. So actually you can see why the walk will, Diophantine walk will behave like a normal walk. Because due to this, when you multiply these probabilities, theta, theta plus alpha, theta plus 2 alpha, you see that the ratio will be bounded. Okay? But this is what tells you how the walk is behaving. Like you say, I want to go from 0 to L and come back from L to 0. If these things are almost the same, it means the walk is behaving like simple random walk. And this is saying this. So kind of contains a little bit the idea of the proof of Sinai's simple random walk behavior of Diophantine walks. When alpha is UV, these products along the orbit can be very wide because there is no solution here. And that's the reason behind our theorem. So here I want to just tell you, there exists a martingale martingale. What is this martingale? You call sigma n is the sum of log pi minus log qi. So now imagine the medium is fixed. So fix theta and look at the one single medium you get, p of theta plus I alpha. You introduce a sum for n positive, and sigma 0 is 0, and sigma for n negative you have the same sum, but it's log q minus log p. So this sum is telling you what kind of resistance or what kind of help the medium gives you to walk from 1 to n. If this quantity is very negative, then it's very hard to go from 1 to n. If it is very positive, it's the opposite. Okay? And the martingale is the following. You introduce nn, it's equal to the sum of exponential minus sigma L from L equal, here I'm going to write a mistake, but okay. Something like this. And now it's m of zt that is the martingale, the magic martingale. Anybody who tried to give a course on probability theory and who wanted to amuse the students with gambler's ruin problem would know that using this martingale really simplifies a lot the calculations of the probabilities. Will the gambler become rich before losing all his money, or usually not, but anyway, if you have this martingale, you thrive, and that's what people do. Higher dimension equivalent of this does not exist, and that's why you stop. Now,
Does not exist or is unknown?
isn't known. I don't know. It's not my specialty. I'm sorry for deceiving you, but it's like this. I can nevertheless try to guess what is behind Sinai's proof as a dilettante. I would say, okay, when the pi and qi are random, this function log pi minus log qi is an IID. So it sums sigma from 1 to t for some times t will be of the order of minus square root of t for t positive and minus square root of minus t for t negative, which means that the walker at this time t meets a barrier of the order exponential square root t. Okay? Which means that the probability for him to reach t is exponential minus square root t, likely. And that's why you get this log t squared confirmation. So the log t squared of Sinai localization is actually due to the usual CLT on the medium. The strong thing, however, is to show, not to show that you have this slow diffusion, but to show that when you divide by log t squared, you do have a limit distribution, let alone computing it later. Okay, just one last 2 or 3 minutes. I wanted to say what? So we get criteria using this sum. Well, first of all, the key thing is that the probability that the walk zt reaches A before B when z0 is equal to n, so you have A, B, and n, will be, due to this martingale stuff, will be like m A divided by nb minus ma, something like this. And this is key. This is the key behind all the calculations. So now you get criteria for diffusion behavior. And what are these criteria? For example, if sigma n is less than minus square root n, and sigma minus n is less than minus square root n, okay, then the t will be less than log n, oh sorry, the t will be less than n for t of order exponential n. You just apply this, yes, and you find that if you start at 1, and the probability that you reach 0 before reaching n, or to reach n before coming back to 0, is exponentially small. You iterate this, and you find that during exponential square root n, you will be less than n. With very high probability. Actually, exponentially small probability to violate this. So this is one criterion. But you also have criteria that will tell you when the walk will diffuse to the right, and other criteria that will tell you when the diffusion will be localized on minus n or on plus n. And the drawing is this, because at the end of the day, there is always just one drawing behind anything. Well, when the thing is simple like this, yes, there is. And the drawing is this. So it's not so simple as when you start doing it in quasi-periodic, but let me just say. So you have the walker, it's on Z. And then I'm drawing schematic log p minus log q as a function of the I. So imagine it's like 0, and then here, and here, somewhere, you get. So now you look at your sums. So this is 0, this is here, it is a n. So you look at the sums from 0 to n, or this is also of order n. If you start here, your walk. No, sorry, you start here. If you look, when you try to walk in this direction, you will see a log p minus log q that is positive. So it will push you to the right. You will get here. But when you are here, if you try to walk to the left, you get sums that are, say this hill will account for something like square root n. But since you try to go like this, you see it as a minus square root of n. So you're blocked. And you're exponentially localized. If you try to walk in this direction, you also get blocked, because you get negative sums. Okay? Because when you go to the left, you sum log q minus log p, not log p minus log q. So you get negative sum. If you go to the right, you get negative sum. So if you start here, you are localized. If you start here, you try to walk like this, you diffuse in this direction. Sorry. Now, if you start here, when you will take the sums in this direction, they will be very negative. So you will never go there. But if you take the sums in this direction, they will be positive. So you will go. And this is how you get one-sided drift for people who start here. People who start here are confined. People who start here have a positive probability to end up here and get confined, and a positive probability to end up here and get confined. So this is it. And you want to do this in quasi-periodic. You want to show that the quasi-periodic walk, the PI, the set PI you get, will have this behavior. And this is technology. Now it's a Liouville technology, you have to have a doigté, but it's feasible. You introduce a function and you use multi-scale analysis. So this is like minus 1 over qn, qn are the denominators. You put a function of this kind, and you show that the probability you get, the function, will have these properties for almost every point. The trick here is that you can do it starting from scratch. If you start from a probability p equal 1/2, 1/2, you can perturb it to make it like this. But what if you want to go further? And so you get just for some sequence of time, a fixed time. But you want to have an infinite subsequence of time. Or you want to have this G delta thing. So you must start with any p and make it look like this. And how you do it like usual in quasi-periodic dynamics. You always get back to the integrable case, to the linearizable case. So you first have a lemma that approach any probability PQ by a coboundary, this like the Diophantine phenomenon. There exists a solution to P over Q equals G theta plus alpha divided by G theta, and then you perturb. Okay, thank you.
Sorry, but no time for questions. And if anyone has any question, ask him afterwards. And then let's take.
If I still have a voice.
And then we will start again in 5 minutes. Usually, sorry for the delay. This is the first day, and we are all.
Porque ele tinha dito que ia falar sobre. Oh, sério. Beleza? So, okay, so this talk is called Metrics Thermodynamic Formalism, and I guess at the beginning of the slides I presumed some knowledge of what thermodynamic formalism does and is for, but I'd like to sort of take a step back from where I started the slides and just talk about classical thermodynamic formalism coming into at least filter through my own interpretations. So, okay, so you have situations in dynamics where you might find it useful to have a symbolic coding of something. So maybe you have a map on the interval which is expanding, that stretches the interval out into two pieces, which are then folded back on top of each other. And you can say, well, you can try and understand the trajectory of something by partitioning, say, space into pieces. And
Excuse me, apparently the people behind are too shy to say that they cannot hear. So you should either speak louder or use the mic.
okay, sorry. So, is this an improvement? It's still too shy. Okay. Is that better?
Yeah.
Okay, right. Good, thanks.
Thanks, Jim.
Okay. All right. So, yeah. So, where was I? Okay. So I was talking about symbolic coding. So, all right. So you can have a very basic situation where you have an expanding map of the interval or something like that, and people sort of it occurred to people at a very early stage that you can partition the phase space in certain ways, and you can then start with a trajectory which belong to this set and then move it forwards, and you notice it goes to the other set, it ends up somewhere else, and you can follow the trajectory at this point and get some sort of sequence of ones and twos or whatever symbols you're using. And you can, for certain situations, you can model the dynamical system very well just using these sequences of symbols. But when you're, this is essentially topological data that you're getting, but obviously there are going to be situations where you're interested in measures on this dynamical system, and you want to try and pull the measures back to your model using symbols. And I guess this is sort of the problem that, or a problem that thermodynamic formalism is intended to solve. So, I mean, for another example, you could have, say, a sort of fractal limit set, which is defined by several transformations. So you start with this set and you map it down to these subsets, and then subsets of those sets. And you have some limit set, which is the intersection of these. And you can, hello? Sorry. You can understand the destinations of points, or you can give addresses to these points in limit set, which are also symbolic sequences. And then you might get into a situation where you want to construct measures on this object, and you want to pull some information back to the symbolic environment, which will allow you to work on that, on the symbolic space, and construct your measures there. So this is the that the sort of classical thermodynamic formalism I have in mind in this talk does. Okay, so you have that preamble done. So you have some number of symbols, and you have a space of sequences. So I'm just going to be looking at the simplest possibility of having all one-sided infinite sequences over these symbols. So okay, so you equip this with the infinite product topology, and it becomes a compact, metrizable topological space. And you can have the map on it, which consists of shifting a sequence forward and deleting the first element, which is what the dynamics will correspond to in this model, or corresponds to going down a scale in this kind of environment. So, okay, so just for notation's sake, this is going to be my notation for the set of sequences which begin with the specific symbols I1 up to IN. and so we have some function which we've pulled back from whatever our model was, which is giving us some sort of dynamical information. So, okay, I've drawn these as straight lines, but it might be something like the log of the derivative of this map, or it might be something like the derivatives of the maps which you're using to contract here. So, in particular, I'm going to make some regularity assumptions which are going to make things behave reasonably nicely. And the sort of classical one is that if you've specified the first n symbols, then you've specified the value of the function to within some exponential amount. And for historical reasons, this tends to be called a Hölder continuous function. So you sort of assume you this kind of regularity for your data. Okay, so the measures that you end up constructing on the symbolic space, this sort of definition turns out to be quite helpful. So you end up wanting to measures which maximize entropy plus the ergodic average. And we call these equilibrium states. So at the moment, while I've written Hölder regularity, you don't really need it to have an equilibrium state. As long as you have continuity, then this is going to be a continuous function of the measure. That's a semi-continuous function of the measure. The measures are compact in the weak star topology. So this thing just exists by abstract arguments. But you often want to know a bit more about it. And the sort of historically interesting thing to find out, okay, fine. So a thing which is useful to know about these is the Gibbs property. So I suppose these two things don't immediately to resemble each other, but in a sense, I think the second one is a bit more revealing. So we're saying that we've got a measure on the symbolic space, and the measure of a cylinder set, of the set of all sequences beginning with a particular string of symbols, is going to be roughly proportional to this thing, which is a sort of dynamical object. So we've got some dynamic information here, which we've brought over from the original system, and we're asking that the measure of a cylinder is going to be roughly proportional to this thing, suitably normalized. So, okay, so for this second one, you definitely want Hölder continuity in order for this property to work. So, okay, so I mean, I could give a whole talk about the applications of these ideas, but there are other things I want to say. But this has historically been a major tool in hyperbolic, maybe a bit less so now. And it's used in statistical mechanics, dimension theory, and all sorts of things. So this talk is really about extending this classical tool in a direction which is not really given by what I've said so far. And in particular, it's about extending in a subadditive direction. So, okay, so with the Gibbs inequality, we had an inequality between the measure of a cylinder set and an ergodic average. So we had a bound of this type, and we had a bound on the ratio of these things. And in particular, this thing, so within a constant proportional, the constant of proportionality, depends only on the first n symbols. So if we want to look at this more abstractly, then the thing to do is to just look at functions on finite strings of symbols, which are going to be sort of surrogates for these ergodic. So, okay, so in particular, I want to look at subadditive objects, or submultiplicative, depending on whether you've taken logs or not. So in particular, I'm just going to say that I have some function from words corresponding to cylinder sets to real numbers, which is going to go down here. And I want to know it's subadditive in the sense that if you apply this function to two words stuck together, that's less than or equal to what you got if you applied it to them individually and multiplied. So I think the sort of archetypal potential I'd like to think about is the norm of matrices, which is given by the symbols that we're using. So in particular, that has this submultiplicative property. So, okay, so we have a function on words. I'm not using this microphone very well, am I? Sorry. So, okay, so we have a function on words, and another way of interpreting that is by defining a particular function which is just going to take an infinite sequence to the value prescribed by the word, which is the first in symbols. And this defines a subadditive family of functions in the sense of the subadditive ergodic theorem. So, again, you could look at that as being this sequence of subadditive functions. So, in particular, you can apply the subadditive ergodic theorem, and you've got a well-defined ergodic average. So then you can just recycle the old definitions and say, so a notion of pressure, we're looking for things which, measures which maximize entropy plus this ergodic average of this potential. And again, that's going to exist for essentially abstract reasons because these things both depend semi-continuously on the measure. So you can just appeal to the compactness of the set of measures. So this thing exists. Like a bit more is to understand their fine structure. And we'd like to know that they have this Gibbs, we'd like to know when they have this Gibbs property that we got for Holder potentials in the classical. So, as with the classical case, the first object uses very little regularity, but for the second one, we're sort of asking for these values to be surrogates for the measure of a cylinder set. So in particular, if you add up the measure of all the cylinder sets of a given length, then you get 1. So you're asking for these values over words to add up in a reasonable way. So you're probably going to need extra conditions to make that work. Okay, yeah, so if you have an invariant measure which satisfies the Gibbs inequality, then it's definitely an equilibrium state, but the reverse is fairly trivially not true. So, okay, so if you want your equilibrium states to have the Gibbs inequality, then there's a handy general result that you can use. And this has appeared in the literature quite a few times over the last 10 years or so in various forms. But essentially, it's just an argument of written in a more general way. So the original additive arguments of Bowen can be recycled into the subadditive context with fairly little loss. So the condition your potential to have is that if you apply it, so if you to finite words and you try to connect them by some interpolation, then using an interpolation of only bounded size, you can recover some sort of approximate multiplicativity. So if you do this, then if you have this, then you get a unique equilibrium state. And you get a Gibbs inequality for the equilibrium state. So this is essentially the same as, it plays a similar role to specification in classical thermodynamic formalism. And this is general enough, you can pull the classical case out just by defining a subadditive potential as a sort of local maximum of the additive one. So, okay, so I might talk a bit about why you want to do this. So So you have some situation, some context which is a priori not symbolic, and you in a situation where you want to understand measures on this dynamical object which are given by some sort of data. So if you have very sort of simple examples of self-similar sets, like the Sierpinski gasket, then you have the property that the structure on smaller scales is exactly what you have on the higher scales. But if you start looking at self-affine sets, where the smaller copies are allowed to be linearly distorted copies of the original set, then passing through the scales in the way which is done for more classical fractals doesn't give you very much information, because you start to find that the sets you're passing down to of going down through the scales according to the different maps we're given to construct a measure which has got large Hausdorff dimension. So, so the sort of reasonable context in which to do this is to assume that we have some region which is preserved by these maps, in that it's mapped within itself by the different transformations we're using. So it'll be mapped down to here, here and here, for example. And these maps, these images don't overlap too strongly. So a sort of natural way to construct a measure would be to just assign a weight to each of these three pieces, and then iteratively proceed down by giving measure to, by defining the measure on these things as if they were cylinders. And I guess with the original Sierpinski gasket, this is one of the ways to construct a measure of maximum Hausdorff dimension, just by giving measure 1/3 to that, 1/3 to that, 1/3 to that, and so forth, and then 1/9 to the smaller pieces. And it specifies a measure on the limit set which has a large Hausdorff dimension. But in the self-affine context, you're dealing with quite distorted smaller images, and it's a bit less obvious what kind of weights you should be assigning to these things. So the method which is thought to work, or which is thought should work, is if you have a particular subadditive potential on the symbolic space, and you use this potential to, or rather you use equilibrium states for this potential to assign weight to these cylinder sets. And this potential should somehow represent the sort of S dimension which these images take up. So if you had conformal transformations, then you could just reduce this to a single number, such actually like the derivative, say the log of the Jacobian or something like that. And then you're back in classical thermodynamic formalism, because the information you to the symbolic space is a single number. So in this case, so we have some linear distortion, so we're going to have to introduce some more matrix-like quantities. So so if you have some linear map in finite dimensions, then you take a round ball to an ellipsoid with the semi-axes are called the singular values of the linear map. And so the reasonable notions of S-dimensional diameter for these circuits are described in terms of singular values. So it is believed that the correct potential to use is for the S-dimensional diameter is to count through the singular value of the linear map corresponding to the subimage, the last whole integer and then multiply through by the rest. And you can express that using exterior algebra as a product of two norms of objects derived from the linear map you're using. So we end up defining this family of potentials where you've got some specified matrices, you've specified some matrices and you're applying this function, which is this product of singular values, to the products given by specific words. And you can define the pressure function variationally as before and look at the equilibrium states of this potential. And you find that the pressure is a concave decreasing function of the parameter S. No, I think I'm okay. Thanks. So you can extract a pressure function of this, depending on this variable S, and you choose the unique value of S such that the pressure becomes 0, and it's then expected that the equilibrium state that you get from that potential should push down to a measure on the limit set with the maximum possible dimension. So this sort of brings me to the problem that I want to discuss, which is just that if you're given a finite collection of matrices and you want to understand the equilibrium states for this potential. So the simplest case is just when we are multiplying some matrices together and taking the norm. So in low dimensions, that's all you need to do. Then if you sort of just do the working out, then the variational principle says that you're trying to maximize entropy plus S times the Lyapunov exponent. Okay, so to get a unique equilibrium measure, what you're trying to do is you're trying to check that this specification or quasi-multiplicativity condition holds. So you're asking that you've got your matrices and you are allowed to take any, so if you take any word of a given length, any word of another length, then you can interpolate them with a product of bounded length and still keep all of the norm, or almost all of the value of the norm. And this is, if you're familiar with these kinds of things, then this is obviously not going to work for all kinds of matrices. So if your matrices are, if they're diagonal, one of them is large in one diagonal and the other one is large on the other diagonal, then you could have one of your words being large on one axis, the other one being large on the other axis, and then you can't interpolate between these with a product of bounded length and expect to get something which is as large as 2 to the n plus m there. So for diagonal matrices, this is certainly going to be false. So, and you can reasonably ask what, well, how you can characterize these equilibrium states as best you can. So, okay, so if you don't have a Gibbs equilibrium state, then this inequality here has to be false for every m and every delta. So if you just divide out by the norms on the right, then you can take some limits, and you end up with this situation that you can construct some non-zero matrices where every word from your original matrices that you put in between those two gives you the zero matrix. So, okay, so this tells you something quite specific. So it says that, so neither B1 nor B2 is the zero matrix. So anything in the image subspace of B2 is landing in some position, and then whatever combination of your matrices you apply, you can't move it outside the kernel space of B1. So, okay, so if you fail to have a unique equilibrium state, then you've learned that these linear maps had a common invariant subspace, which you can write down explicitly, and it's not a trivial subspace. So, and yeah, so as well as that, you can sort of say, okay, so this condition is so this condition is also true for matrices in the algebra generated by your collection of matrices. So, all right, so if you're in this situation, then you've got some invariant subspaces, so you can simultaneously block triangularize your matrices, and then you can do this in a maximal way where the matrices on the diagonal don't have any invariant subspaces. And we're trying to maximize entropy plus Lyapunov exponent for this thing. And so, okay, so I guess who work with this stuff a lot will realize that if you put in a ergodic measure into this and you look at the Lyapunov exponent, then the top Lyapunov exponent of the original object is just the sum of the Lyapunov exponents of the diagonal objects. So you can create some new potentials using these diagonal blocks, and the equilibrium states of your old potential are just going to be necessarily going to be equilibrium states of the smaller potentials given by the action on the invariant subspaces. So, yeah, so you just use it playing around with the subadditive ergodic theorem will give you this fact. And in particular, because this decomposition was minimal, these submatrices don't have a common invariant subspace. So you can run all the previous argument and find out they have to have a unique equilibrium state each. So this gives you a bound on the number of equilibrium states. It tells you that they're all Gibbs with respect to certain subpotentials. And it gives you a complete description for this equilibrium states of the norm. So, okay, so what about the... Oh, yes, and these are due to Deja and Feng and Antika and Maki. So, what about the more complicated case? So, in this situation, you're looking for the same sort of interpolation property. And you say, well, what if this fails? And you can rewrite this object as this slightly horrible product of norms of exterior powers. But all you really have to do is just apply the same limit argument, and you end up constructing a pair of linear maps on the exterior powers. And in this case, this product of two norms has to be 0. So you end up in a situation where for any word that you put in, any matrix product you put in, either this equation on one exterior power holds, or you get an equation on the other exterior power. So this is a bit more messy, and in particular it doesn't tell you anymore that you're in a special subalgebra of matrices, but it tells you that your linear maps belong to an algebraic subgroup of the invertible D by D linear maps. And by tweaking this a bit, you can, by looking at this rather carefully, you can show that if you don't have specification, you don't have a unique equilibrium state, then you can deduce from the equation I just showed you that you have a failure of strong irreducibility in one of the exterior powers. And that's a theorem I proved with Antika and Maki quite recently. So in particular, if you don't have the algebraic degeneracies at all, then in the most general situation, you're just going to have a unique equilibrium state for your matrices, and it's going to have a Gibbs inequality. So if you're in the situation where the linear maps defining your self-affine fractal are sort of in general position with respect to each other, then you expect this construction to give you a unique measure which has the Gibbs inequality. So in the very general case, it's quite a complicated statement, but so in the low-dimensional case, we had that situation where if you don't have a unique equilibrium state, then you can block triangularize the matrices and derive equilibrium states from the action on invariant subspaces. In the general situation, you end up doing something which is thematically similar, but a lot more complicated. So if you don't have a unique equilibrium state, then you end up with some invariant finite subsets of the product of two Grassmannians on some exterior powers. And you can find that all of the ergodic equilibrium states end up coming from the action of exterior powers on these finite subsets. But you get some general out of this. So in particular, you get a bound on the number of ergodic equilibrium states, and you have this explicit description through the Gibbs inequality, and it tells you in particular that they're always fully supported. So, okay, so in 2 dimensions, you don't have to do the harder case. You can write everything just as a norm to a power. So the arguments of Fung and Kahn-Markey are sufficient for understanding that. And in 3 dimensions, there are not too many cases, and that case was solved by myself and Antti Kahn-Markey a couple of years ago. And the general case is due to myself and Jaroboki, as it said on the last slide, but I'm not sure if I actually said that. So the bound for the number of ergodic equilibrium states is probably not sharp as presented there. So in low dimensions we have we know exactly how many ergodic equilibrium states you can get, but in higher dimensions this is still conjectural. And okay, so in the classical thermodynamic formalism, there's a huge amount known about the properties of equilibrium states, like having the Bernoulli property, exponential mixing, and things like that. But these things have not been explored very much for matrix equilibrium states. Existence and uniqueness are still sort of active problems, so stuff like that will come later. Okay, so yeah, so I can give certainly one explanation for this characterization of equilibrium states with Jaroboki. Okay, so if you have a self-affine fractal, so if you have a fractal limit set which is made up of linearly distorted copies of itself, then okay, so then there's a quantity defined by Faulkner, which is just the unique value of the parameter which makes the pressure function defined by Faulkner to be 0. This is conjecturally the equal to the Hausdorff dimension of the limit set. And so Jörg Schmeling asked in the 1990s, in what cases the Hausdorff dimension of a limit set defined by a set of contracting maps is reduced when you just throw one of the maps away. So, for example, if you're in the situation of the classic Sierpinski gasket, then you have 3 maps giving you copies of the set. Tractor for the 3 maps is the Sierpinski gasket. But if you just throw away one of the maps, then you have only 2 maps left, and the limit set is a line, which obviously has lower Hausdorff dimension. But if you don't have conformality and you have these linearly distorted copies, then this is actually a much harder question. And I think there'd been very little progress on this question for affine iterated function systems, despite the sort of obviousness of the statement. So clearly in any reasonable situation, if you throw away one of the maps, then I don't believe so. I think this question is still an interesting question for other reasonable notions of dimension. And I picked Hausdorff dimension because that's closer to the themes of the talk. But I think for box dimension or packing dimension or anything else, it's also an unsolved question. So, okay, so using our work on equilibrium state of Falconer's potential function, Jairo Bocchi and I were able to give a sufficient condition for this thing to happen. So I'll say that this is Schmelling's property if removing one of the maps which defines the limit set reduces the Hausdorff dimension. Okay, so yeah, so what we were able to prove using this is that if you have an affine iterated function system defining one of these limit sets and the Hausdorff dimension is equal to the value conjectured for it by Falconer, then this does have Schmelling's property. And this, the proof of this is using the fully supported nature of the equilibrium states. So if Schmelling's property doesn't hold, then that means that at this critical value of the pressure, where the pressure is 0, then if you throw away one of the maps, then you still have pressure 0, which looking at that alternatively, you can say if you're throwing away one of the symbols, you retain the same pressure. But if that works, then there has to be an equilibrium state depending only on the first n-1 symbols, which is still an equilibrium state for all of the symbols. And that's the same as saying that it's an equilibrium state supported on a shift on fewer symbols. But my theorem with Jairo Bocchi shows that the equilibrium states are fully supported, so this small equilibrium state can't exist, and you get a contradiction. Okay, so, yep. So I think that's about the end of the talk. So also thanks for putting up with the microphone, solve my use of it. Yep, so the value conjectured by Falconer for the Hausdorff dimension is known to be an upper bound. So it's getting the lower bound, which is the difficult bit. And there are also known examples where it's not where the Hausdorff dimension is less than the upper bound.